right, we're looking at section 6.4, arc length, which is using integration to find the length of curve on the xy plane. And the book gives us, for arc length, 3 formulas in boxes. But really, those formulas can all be boiled down to this. The length of an arc is the integral from a to b of the square root, and square root comes from a distance formula here. The first thing is dx, the derivative of x with respect to something squared, and then the derivative of y with respect to that same something squared, and then we're integrating with respect to that same something, whatever the something is. And also, something ranges from a to b in values. Okay, so sometimes our something is t, and that happens when we have parametric equations, where you have x expressed in terms of t and y expressed in terms of t, and then you have the derivative of x with respect to t, derivative of y with respect to t, and you're integrating with respect to t. Or sometimes you have that something is an x, and that's when you have a regular plain old function y equals f of x. So your derivative of y with respect to x is the normal derivative. Your integration is with respect to x. And then this term, dx dx, the first term here, just becomes a 1. Derivative of x with respect to itself is 1. 1 squared is still 1, and you have 1 plus in the formula. And then the last thing that might happen is if this is a y, that happens when you're given a function x equals a function of y, and then we have dx dy, which looks a little weird, but it can happen, squared. dy dy is 1, that's squared, so we have a plus 1 under our square root, and we're integrating with respect to y. Now if you look at our problem over here, x equals y to the 3/2, this is x equals a function written in terms of y, so we are in this third case. And y ranges from 0 to 1, so those are our a and b values. So to set up this problem, we get the arc length is the integral from a to b, 0 to 1, of the square root of y, so we have dx dy squared plus dy dy, which is just 1, squared, and then we're going to integrate with respect to y. Okay, so I need to find what's the derivative of x with respect to y, and that's just our plain old derivative. It just looks a little different. So if I take x is y to the 3/2 and do the derivative, well, y is treated as the variable of differentiation, bring down the 3/2 power, write my y, the new power is 3/2 minus 1, which is 1/2. This is my derivative, and I plug this into the arc length formula. 0 to 1 of the square root of 3/2 y to the 1/2 squared plus 1. Okay, so we might want to clean this up just a little bit. When I square something in parentheses, I have to square both pieces. So squaring the 3/2 gives us 9/4. And then y to the 1/2 squared, well, that's just y plus 1. And now this is actually going to be easier if I factor out that 9/4. So integral from 0 to 1 of the square root of 9/4 y plus, well, then I'll have 4/9 left there, dy. And pulling it out means I can pull it all the way out of the radical sign. I can take its square root, this fraction's square root, so I can pull 3/2 out of the radical sign. And if I'm pulling it out of the radical sign, I might as well pull it all the way out of the integral. And I'm left with the square root of y plus 4/9 dy. Okay, that's something we can integrate. So this is 3/2. This is y plus 4/9 all raised to the 1/2 power, so I raise the power by 1 and divide by the new power, or multiply by its reciprocal. Leave the inside alone, And, ooh, if there were a derivative of the inside to worry about, then I might have some nasty U substitution. But in this case, the derivative of the inside is just 1, so this is easy. And I'm evaluating from 0 to 1. Oh, this is really nice. The coefficients are all canceling. And I just have, well, let's plug in the 1. So I have 1 plus 4 ninths. 9 ninths plus 4 ninths is 13 ninths raised to the 3 halves power minus, plug in 0, and I just get 4 ninths raised to the 3 halves power. And that's the answer. Now I can clean that up a little bit and make it, these are cubed and also square rooted. So I can do the square roots. Square root of 9 would be 3, and then cubing that is 27. I can't do the square root of 13 though. So if I had the square root of 13 cubed, that gives me 13 root 13. And over here, the 27 on the bottom again, and then 4, the square root of 4 is 2, 2 cubed is 8. And so I can combine these a little bit, and if you had the back of the book's answer in mind, it has it in this format. Okay, so that would be my final answer. This is the length of the curve, x equals y to the 3 halves power, when y ranges from 0 to 1. I can also take a second to talk about the different forms of the answer. So this last one is what we would call the final answer. This is an exact answer. As opposed to a decimal value. This is an exact value. If I plugged it into a calculator, I could get a decimal value, but we generally like the exact one better. If I gave you this answer up here, we would say this is set up the integral, but for whatever reason you might be asked to set up the integral and don't solve. And then this, maybe a different kind of bubble, jagged bubble, this version of the answer where you've taken the integral and you've done the fundamental theorem of calculus and plugged in the numbers and stuff here, this is what we would call a calculator ready answer. So on an exam, we might ask you to find what's the calculator ready version. All right, hope that helped. Zoom back out so you can see the whole thing.